Which team are you looking at doing? Which team are you looking at doing? What is the oh, that's cool. Go ahead and buy him.
Good morning. Give me a minute here.
Oh, you?
Well, they said it'd be before class today.
Oh.
Let me begin. Good morning. Glad to see all of you here bright and early on a cold day. I want to make a few announcements and then we'll get going. First of all, I'm just curious how many people subscribed for the ZY Books version? A dozen or so, maybe. Okay, sounds good. I'd be curious what you think of it after you've tried it for a while. Office hours are, I will post the Zoom link on Canvas after class, so you'll be able to touch base with me after class at 10:10 is when I start my office hours. My plan is to schedule all of you to meet with me on a one-to-one basis for about 15 minutes during those office hours. And since there are, I'd like to meet with all of you before spring break. And if you calculate how many slots there are, I'm going to have to add some office hours, which I will do. And what will happen is you will get a Google form where you'll fill in which time slots work for you to come meet with me. We'll meet over Zoom, but if anybody wants to meet with me personally, not by Zoom, but in my office, we could do that, but that's by appointment only. We'll have to figure out when we can do that. I just got a big air filter in my office, and I'll just have to figure out where to put it to get the best air circulation going. You'll also notice on Media Gallery on Canvas, you will see all recorded lectures. And you'll notice there are two versions. One is a side-by-side format, and one is just a single format. A single pane, if you want to call it that format, is pretty much just going to have my voice and the slides. If you want to see me, then you need to do the side-by-side format, where you will see me and the slides in the two panes, okay? One pane will have the slides, the other pane will have me. And the reason I bring that up is I am going to be using my arm as a robot along the way, and there are times that it might be useful for you to see what I'm doing by gesturing on my arm, on my hand, on my wrist, etc. So otherwise, I don't really care if you look at me. I have no interest in that. But I think it will be useful for you to see that and go back and take a look at that in order to understand some of the joint angles, some of the coordinate frames. I would literally get up and use my body as a coordinate frame just to try to explain some of the things. So again, the side-by-side version will let you see me. The other version just shows the slides, and you'll hear my voice. So anyway, I'll post the Zoom address for office hours after class today. Is there someone named Hayung Jeong here? Hayung, H-A-Y-O-U-N-G. Jeong, last family name J-E-O-N-G. Okay, because he did not submit the Google form for scheduling a lab. That's why I'm asking. Is Timothy Dorn here? Okay. I haven't yet heard from Miranda down in the, she's going to form the lab groups. I think there should be no problem. Let me check with her during the break. And my plan is to post during the break after the first part of this class, sometime around 9 o'clock. When I stop talking, I'm going to check if Miranda got your name in there, and I know exactly where she's going to put you unless it doesn't match your available slots. So I will post that on Canvas again, so you'll see exactly who you're meeting up with. And the plan is that you should look up that person's email address, contact them, and then you can exchange cell phone numbers so you can text each other and do whatever you need to meet up. I find that people today don't pay attention to email. They pay much more attention to text. So I leave it up to you how you get together and schedule everything. So the plan is to post the lab schedule during the break today. So my understanding is that Nick Arsvold, who is the teaching assistant, is going to present on the first lab. And so I am going to open up a Google. Let's see if this works. I haven't done this. Sign in. Oh, okay. Let me do that. Okay, that's me. Okay, there is Nick. Nick, you're muted now. You can unmute.
I believe you're muted, Professor.
Huh? I can hear you. And everybody can see you too. I'm muted. Okay, I'm unmuted.
All right.
You're on.
All right. Good morning, class. Sorry I'm not with you in person. Would love to be there, but unfortunately I came down with COVID. But I'm still excited to be your TA this semester, and excited to work with you as soon as I get healthy. So, Professor, I believe right away into the presentation for Lab 1.
Yep, go ahead.
Okay.
Oh.
All right, let me... All right. Are you seeing the correct slide, or are you seeing the presenter view?
The presenter view.
Okay. Better?
Yep.
All right. So, as I mentioned, I'll be one of your lab TAs. I believe you met the other ones on Tuesday. And I'm here to present our first lab, which is just going to be an intro to the robotics lab, how to use the robot, how to familiarize yourself with the software. So today we'll be going over what the lab is, an intro to the robot, the lab description, as well as some logistics that we have to consider, especially with the ongoing pandemic. So our lab is located in the old side of ME, in the basement, so ME 74. Luckily, they just reopened the west end of the building, so it's easier to get there, so you're not going to have to walk around a lot. Our lab has 2 robots that are active at a time, and there's going to be 2 partners. So there's going to be 4 people in total in the lab usually. However, there's also a 3rd robot, which is going to be used for makeup assignments. So for example, if a group has come down with COVID or another, or for whatever reason can't finish their assignment normally, they'll be able to come in the following week to make up their assignment. Before each lab, students must fill out a check-in form, which is on the website. Pretty much that's just making sure that there's multiple people in the lab for safety reasons, that everyone's wearing a mask, as well as their safety goggles. And then also on the website, there is the calendar to schedule additional time. And on that you can see our 4 TAs that will be working with you this semester. Evan, Nate, and I will be working primarily with the lab, while Robert will be helping you study and prepare for the tests. So there's been a lot of change to the lab this year. We used to only have 4 labs. Now we have 5 labs and a demo. So it's going to be quite full. The first lab, which I'm presenting today, is titled Hello Cobot World. It's going to be 1 week long. So that's going to be next week, Monday through Thursday. Students are going to be working on it. It's going to be the introduction to the robot. Lab 2, we're going to go over straightness and repeatability, terms that you'll learn here in the next few weeks. Lab 3, you'll be using a robotic gripper and learning about transformation. Lab 4 is kind of our biggest lab. It's going to involve using all the stuff that you've learned up to this point to put together a small flashlight using the robot. Lab 5 is a whole new lab that we've put together, which is going to incorporate cameras on the robot. So we're going to do a little bit of computer vision. And then the last week is going to have a demo, in which the students are going to learn about impedance control, which is a topic that you'll learn throughout the semester. You won't be implementing it, but you will be trying it out to see how it works and really getting a feel for things. So lab deadlines, your memos or reports are going to be done individually, and they're going to be due 1 week after your lab is complete. So for example, lab 1 is going to be done next week, and so the lab 1 memo is going to be due 2 weeks from tomorrow. And that's due on Canvas at 8 a.m. And for most of the labs, it's just going to be a memo, which is going to be a page or 2 long. However, lab 4 is going to have a full lab report, as well as a demo video of your flashlight assembly. So safety is something that we're definitely considered throughout the construction of the lab. So 2 people must be present at all times when operating the robot. This is a must. You really can't go in there and work alone. It's not safe. Also, we want you to use common sense and don't get in the way of the robot's task while it's operating. You can make adjustments on the table when the robot is stationary, but don't try to move things on the workbench when the robot is moving. And when you're operating the robot, one person must be in control of the emergency stop at all times. It's just good safety precaution. And then safety glasses are to be worn. They're provided. There's a little, there's a container that has them all in there. There's also going to be cleaning solution. So please clean them after you're done. Try to keep things as clean as possible. And then also, like in all university classrooms, wear a mask, stay distanced. We have a divider between you and your partner, so then you're not right on top of one another. But be smart about things. If you need a sip of water, do it quickly and put your mask back up. No food in the lab, also that. Then we have this safety video. Right. All right, let me know if you can't hear this.
Hello class, my name is Nick and I will be your lab TA this semester. On behalf of the entire ME 5286 robotics teaching staff, we welcome you to the lab. In this lab we will be working with robots such as this one, which is a UR5 collaborative robot by Universal Robotics. What I mean by a collaborative robot is it has sensors and safety rated software which work together to prevent damage to the robot itself, you the operator, as well as anything else it does not intend to make contact with. I have a demonstration set up to show how this works. On the front of the robot, we have this aluminum bumper mounted. I'm going to command the robot to move in a straight line towards me. However, in the way is this aluminum plate acting as an obstruction. The robot is going to keep moving until it makes contact with that plate. It's then going to realize that there shouldn't be something there and immediately stop to prevent damage to itself as well as anything it makes contact with. Here you can see that. So you can see the robot stopped as soon as it made contact with that aluminum plate to prevent damage to itself and the plate. Now, an error also appeared on the screen saying exactly what happened. We can then re-enable the robot and it's back to working again. Now, just because it has these safety features, it does not mean that it can't damage you or anything else. The laws of physics still apply, so if the robot is moving with a greater speed, it will carry a greater momentum, and then that in turn could be passed to you in the event of a collision. Here we can see that exact same thing, that same program, however done at a faster speed. If you couldn't tell, that was a much larger impact. The robot reached its protective stop and shut down to prevent damage to itself and anything else. However, the robot is not damaged even after that collision. I can restart it. And then it's operational again. In addition to the safety features built into the robot itself, there are several other precautions we're taking in this course. We wear safety goggles to protect us, as well as face masks to prevent the spread of coronavirus. In addition, we have plexiglass partitions between you and your partner. We have air filtration systems between you and your partner as well, which filter out aerosols from the air. We also work to keep the lab extremely clean. We are really excited to have you this semester and look forward to a great hands-on educational experience. If you have any questions regarding the lab, feel free to reach out to me via email. I hope to see you soon. Thank you very much.
All right. Yeah, safety is key in the lab. We are very, very adamant about keeping things clean and hoping to keep you all safe throughout the semester. And then just here's a close-up of that little test we did. This used to be part of the Lab 1 experiment where we'd actually measure the difference in force at different speeds of the robot. But that's something that we just cut out due to time constraints, as well as we never got our data as good as we wished. So resources regarding the robot, here's the class website, which you've probably heard by now, merobotics.umn.edu. On there you can find the manuals for the robot, the manual for the scripting language that the robot uses, as well as help for different softwares that we use, including RoboDK and Python. If you haven't learned code in Python before, you'll know by the end of the class, that's for sure. So here's the robot we're going to be using this semester. It's the UR5, which is a collaborative robot, which, Professor, have you explained what a collaborative robot is yet?
Just initially, I will spend a little more time on that still.
All right. So in short, it's a robot that's meant to work alongside humans. It's got safety-rated software and sensors to know whether it's made impact with something, to keep the operator safe. This specific robot has 6 degrees of freedom, so that can be generalized as X, Y, Z coordinates, as well as rotations about the X, Y, and Z axes. It has a pose which is defined as position and orientation. So where it is in space, as well as how it's turned in space. The total reach is 850 millimeters. So the furthest it can reach away from its base is that 850 millimeters, so just under a meter. It can lift 5 kilograms or 11 pounds. And then it can also be commanded to have joint movements, which go through joint space, or linear movements in Cartesian space. The difference between those, if it hasn't been quite explained, it is, and you'll see, especially in Lab 1, these linear movements, the end effector moves in a straight line, while the joint movements, it can go in a curved trajectory. It just is a different way the math works out, and you'll get to experience that firsthand in this lab. As far as controlling the robot, there are several different ways that we do it throughout the semester. The first is using the Teach Pennant. It has Polyscope, which is its built-in visual programming. So you can see that right there, where you can move it. You can also add different parts to the program, different movements. You also can use URScript, which is a more detailed scripting language. It's pretty similar to Python in the syntax, although the commands are a bit different. So this is also how Polyscope looks. So for example, the lab will walk you through how to do this. How to program the robot, starting from hitting program robot to adding commands, adding waypoints. You can see the command tree, so you can rearrange the order in which different things are done. I'm not going to go into too much detail because the lab manual does a much better job of describing some of this. And then we also use RoboDK, which is a third-party robot simulator. In it, it has another graphical user interface, where you can drag and drop different movements, which you can kind of see on the screen. It's on the left-hand side of the tree. You can see under task 2, it has these move J's, which are joint movements, and it can go to different targets. But then you can also program it in Python, which you can see on the tree as program 2. And you can use those to work together. Yeah. So you can have some movements done using the graphical user interface, and others you can script in Python. And then there's also several ways that RoboDK can interact with the robot itself. It can have both online and offline programming. The online programming connects via the network to send commands to and from the robot, and it will appear on your PC screen in real time. The other option is to post-process the code, which takes your Python script, it translates it to URScript, which is the scripting language for the UR5, and then it can be uploaded to the Teach Pendant just via a USB stick and ran natively on the UR5 itself. And so here's some images of the RoboDK graphical user interface. These screenshots are taken straight from Lab 1. So you can see that you can add these targets, which are poses that we are going to command the robot to go to. And then we can set different movements to it. So we can have it go to target 1, where it goes to this specific place and orientation, and then over to target 2, 3, and back to 1 in a straight line. You can also change it to a curved trajectory. And on the right, you can see how targets are defined, where it's by position and orientation, which you can see in these colorful boxes here. These numbers represent the offset from the robot base. So the base is where it's mounted to the table. So we can see that this target 1 is negative 575 in the X direction, negative 350 in the Y direction, and 300 millimeters in the Z direction. And then these are the rotations as well. You can have a pose defined by its position or the joint values of it. So at the bottom, you can see where it's defined by the joints. Now, the serial manipulator, what I mean by that is each joint is consecutive from one another. You can change each joint individually. Mind you, that's going to change the Cartesian position. And then here is how the Python API looks like. On the command tree, it's going to appear as this little Python symbol. And then here is some Python code. So we can define our targets either as a pose of values, an array of numbers, or we can have them defined in the RoboDK graphical user interface and can import them, which is what you see right here. We tend to have a home position that the robot always goes back up to, where the robot is straight up and down. But other than that, it's normal Python code if you've used it before. So you have your normal for loops, while loop, if statements. So it should be fairly easy if you know Python. And if you haven't learned Python but know other programming languages, Python's a really easy one to pick up. There's some good YouTube tutorials if you need help with that. So for Lab 1, the first 3 tasks are going to be to move the robot through 3 specified poses in 2 different ways. So we're going to go through the Cartesian space, which is going to be linear motions, which are generalized as those move L commands. As I described, that's going to move the end of the robot in a straight line through those positions. And then we're also going to do in joint space, which isn't necessarily going to be in a straight line, but there are some other advantages to moving through joint space too, especially when we talk about singularities, which I don't believe the professor's taught to you yet. We'll be doing that using the 3 different programming methods and outlines. So that's going to be Polyscope, which is going to be done on the Teach Pennant, the RoboDK graphical user interface, and so that's going to be building your program by using different blocks on the RoboDK interface, and then also coding in Python. And some of that code for the Python has already been done for you. It's on the website, just to help get you started. And then task 4 is going to be where you create a program that traces 2 virtual boxes to explore the robot workspace. So the first one's going to maximize the robot's workspace in the Y direction. So that's going to be the length of the table. And the other is going to maximize the robot's workspace in the Z direction. So that's going to be going up tall above the table. And for that, you can use whichever programming method you most like. A lot of people tend to like the graphical RoboDK programming right away. Throughout the semester, you'll be using a lot of the Python, though. So the deliverables will be an online submission due February 5th at 8 a.m. You're going to have a zip file that is titled your last name and your first name with helloworld.zip. In it, you're going to have all the files that you use, so all your RoboDK files, Python files, and Polyscope files. And then, see mistake here, I'll correct it. You're not going to print it, but your lab report is going to be memo format, 12-point font. There's going to be an example on Canvas I'm going to upload as soon as I'm off this call. And then, yeah, you're going to want to answer all questions in the lab manual on the memo. There's also going to be a post-lab survey, which I'm going to post to Canvas. It's very important that you guys finish the post-lab survey. We've changed up quite a bit of stuff this year, and we want to see how effective it's been. We want to monitor what's working and what's not. We don't want you all to be spending hours upon hours on the pre-lab and then get to the lab and nothing works as expected. So that's your chance to give us feedback. We're going to want that before we publish the grades for the Lab 1 memo. That will be posted to Canvas as well. Late assignments, we don't really do too much for late assignments here. You can turn in an assignment up to 24 hours late. However, the grade will at most be 50% of the total grade possible. So I don't like giving out 50s. So please turn in your assignment on time. We'll do our best to remind you on Canvas, and in class the day before it's due, but at the end of the day, it is your responsibility to make sure that your assignments are in on time. Canvas will be where we publish most announcements. It will have the most up-to-date information. So for example, if a robot isn't working, it stopped working in one lab section, we'll throw an announcement on Canvas to say, hey, robot 2 is not working currently. We're working to fix it. We'll let you know as soon as possible. That way, if something's broken, we can work with you to reschedule lab time or get things working. Additional resources can be found on the course website, murobotics.umn.edu. And then if you need to schedule additional lab time, you can add it to the Google Calendar, which is on the course website. And then edit the event for an open time slot on the calendar. Most of those will be Friday. Fridays have been reserved for scheduling additional lab time. And then here are a couple just tips to help you with the lab. You'll want to bring a flash drive to transfer programs from the lab computers to the Teach Pennant, and from the Teach Pennant back to the lab, your laptop or the lab computers. As always, back up your stuff on Google Drive. It's quite a lifesaver when you have a hard drive fail or your laptop battery dies. It helps you, get your files down. And then save backups of all your programs. RoboDK used to have a problem. I haven't encountered it for a while, where it would delete some Python code, where you'd have it in the program tree and it would just disappear. And then the Teach Pennant has a limited amount of storage, so don't try to just keep your stuff on the Teach Pennant. We'll dock you points if you leave it there. Other students can delete it. So if you have your script code, also back that up as well. And then prep your code in advance. You're not going to finish the labs if you walk in without doing the pre-labs. You should have your code pretty much finished by the time you get to lab. So then on the actual hardware, it's going to mostly be debugging. And then use the resources page. There's quite a few tips that will help with the assignments. I TA'd this class last year, and I took the class the year before that. And so whenever there's something that another student is like, hey, this really helps, we try to update our resources page with those tips. And then office hours. My office hours are going to be Mondays at 9 a.m. They are going to be, I believe, virtual again this year. And so it might take additional time to troubleshoot. Have your laptop ready with RoboDK running, with your code running on the simulation. And then any notes of what's gone wrong. So then I can help you, I can help problem solve some of the stuff, give you tips on how other students have done it in the past. And the other lab TAs will be able to help too. I'm not quite sure when they decided their office hours might be. I don't know if they're by appointment or... Professor, do you know what was decided for that?
I'll have them basically announce something to the class.
Okay, sounds good. So, just know that if, office hours are there to help you. We're your friend. So for Evan, Nate, and I will be able to help with the lab, and Robert can help you prepare for the exams as well.
Nick, given that you have COVID, are you planning on being in the lab Monday morning for your lab office hours? I don't know what your quarantine situation is and how you're feeling.
Yeah, I mean, I'm feeling mostly good. If you can't tell, I have a bit of congestion, but otherwise that's the only thing. I think the CDC guidelines have said 5 days after you catch coronavirus, you're able to go out again while masked. And so I started feeling ill Sunday, so that means Friday, Saturday, I should be able to go out again, but I'll take all the necessary precautions, wearing the surgical style face mask. And then also, since they will be remote, I'll be alone in the lab the entire time.
Any questions while Nick is still connected? I just want to add that we will have clean, fresh surgical masks in the lab. There should be enough for everybody here, so just want to be sure that when you come to the lab, put on one of our clean, dry face masks. You can put it on top of your face mask if you prefer, or you can replace your face masks. I'm told that many people don't clean their masks if they're cloth or they are using old masks. So we're providing a clean, fresh mask in the lab. Use it, and when you leave, take it with you. Don't leave it in the lab, all right? I've also ordered for facilities management to do a good cleaning of the lab. To be perfectly honest with you, the other day I basically emptied the waste paper baskets in the lab. So if any of you find that the lab isn't as clean as you expect, you let me know, and I'll beat up on the right people to get it cleaned up. Now, I do again want to point out a couple of things. Nick, it's okay if you sign off. I'm okay with that. Just want to point out a couple of things. Essentially, we're going to talk a lot about transformation matrix and coordinate frames. There are many different conventions. And one of the things I want you to begin to understand is that not everybody uses the same convention. So one of the things I hope you're going to walk away from in this class is an understanding of the differences between the different conventions. And you can basically, at the end of the day, decide on whatever convention you like. But typically, I can tell you right now that the Universal Robotics people use a different convention than the one I like. I will explain why I like my version, so you can get an understanding of that. But you'll find that the UR5 convention is different. RoboDK is pretty good. It will allow you to use whatever convention you like. You can set that up within RoboDK. Very important before you come to the lab is to do the pre-lab. There are robot manuals on the website. There's Robot 1, Robot 2, and Robot 3. And if you look carefully, the manuals are a little bit different for each of the 3 robots. There are minor points, but if you end up using, we aren't going to assign which robot you're going to use. You will use either Robot 1 or Robot 2. You will not use Robot 3. Robot 3 is just set aside for if there are COVID situations and we need to have some makeup. That Robot 3 will be used for that purpose. So you'll use either Robot 1 or Robot 2. I highly recommend that if you start on Robot 1 or you start on Robot 2 and you need to do a makeup time, you need to schedule a makeup time using Google Calendar, use the same robot. Each robot has slightly different variations. They're machines. They're mechanical devices. And you will find that just because RoboDK, you program in RoboDK, and you end up with a program that does A, B, or C, when you actually get to the real robot, it will not be exactly at the same position and orientation that you programmed in an offline system like RoboDK, and you're going to have to calibrate your program based on the real McCoy. Okay? So if you've already done that and spent 2 hours, if you're going to come in on another day to finish up your lab, use the same robot because, again, Robot 1 and Robot 2 have slightly different variations. Questions about that? Okay. Couple of other things. I do want to get to know what you really look like behind the masks. So I'm going to be sending out a Google form for you to submit a head and shoulder shot picture so that, you know, just basically you're, so I can see what you look like without a mask. And I think I've just, okay. All labs will begin on Monday after the official lab office hours. Lab office hours will always be Monday mornings. They will always be Monday mornings. And I believe we're going to use the same Zoom channel for all office hours. So whether they're a lab office hours or my office hours, it's the same Zoom channel for an office hours. The trouble with the Zoom channel for office hours, they're usually designed for one student entering the room at a time. And it may be more useful to not use that particular kind of Zoom channel. And if that becomes the case, then we're going to use the Zoom channel we have for lectures. So I'm hoping that we don't have to have a million different Zoom links. There will be 2 Zoom links, one for office hours and one for lectures. And they're set up so I can use them anytime. I just obviously have to let you know when to join the Zoom conversation. Any other questions? Again, labs will always start on Monday. They will always end on Friday because over the weekend we change the setup so that when you come in the following Monday, you're going to start on the next lab and then again the next lab and so on. The only time we don't change the setup if a lab spans 2 weeks or 3 weeks. All right? And the memos and lab reports are going to be due 1 week after you finish the lab. All right? So if you finish a lab Friday, they're not due that Monday. They're due, you have another week to sort of get your thoughts together and submit whatever you need. Again, all deadlines and timelines are posted on Canvas. And if you look carefully, we actually tell you how much each memo and each report contributes to your final lab grade. Anything else? Let me see what time it is. Yeah, let me now go back. I'm going to stop this. I'm going to end this Zoom lecture, and we're going to go back to the normal class operations. Okay, it's great. All right, let me quit that. And let me close that. And we're going to go back to here. There we go. All right. When we were last together, this is where I was the other day. Okay. Let me blow this up. All right. So now you can see. Okay. All right. So right now we're going to continue our discussion, and about 9 o'clock, that's another 10 minutes or so, we'll take a break for 10 minutes, and then we'll resume after that. So let me come back to what we were talking about the other day. We have a number of sensory modalities that we as humans use, and in some sense, robots are designed to mimic. Mimic doesn't mean duplicate exactly. It basically means trying to copy based on our best understanding of how humans do it. So when we talk about vision, we have our eyes. Now, I should point out, and I assume most of you know this already, that besides our ability to take in all the colors and take in all the blobs, if you will, I mean, we're certainly able to distinguish where one thing ends and another thing begins. We're able to distinguish and identify tables and chairs and people. And we do that because we've learned that. We've developed some common sense about our understanding of what's out there in space in front of us. But besides that, we have 2 eyes. And because we have 2 eyes, we have what you might call stereo vision, and we can recognize depth. So we are able to figure out how far something is based on our ability to use 2 eyes and, if you will, triangulate. Now, you're going to wonder, you can close one eye, and you still have the ability to figure out how far something is in front of you. And that's because over time, you've already learned to some extent about how things sit one behind the other, and you've already learned scale. You've been able to scale things based on your understanding. So even when you close one eye, you're still able to sort of figure how far things are. All of you understand, cameras, autofocus devices. Autofocus devices use the ability to use two images and then find the same spot in both images and then calculate how far things are and use that to help focus. Now, obviously the cameras in here, again, the higher the quality of the camera, the more lenses there may be, and there may be all sorts of extra stuff they do in software to compensate for lens quality. But the bottom line is we use vision to do lots of things, like figuring out that, hey, the microphone, where is the microphone? I forgot to put it on, and I'm able to recognize where it is, pick it up, and then manipulate the microphone so that I can stick it on my shirt in an appropriate location. But we have to duplicate that using a camera on a robot. This year is the first time we've integrated vision into the laboratory. That will be lab number 5. And we've purchased essentially cameras that are installed at the wrist of the robot. So essentially you have to kind of move the gripper out of the way, so to speak, and then use the camera that's on the robot in order to figure out what's there. And again, that camera on the robot, it has limitations, and you're going to learn that cameras aren't exactly. First of all, it depends on the quality of the camera, the quality of the lens, the resolution, etc., etc. And you'll learn that using a real digital camera for positioning things and identifying things in the lab. That lab will take place after Rodney Doctor does his lectures on vision. So again, we've partitioned all the lectures. Rod Doctor will do the presentation on computer vision, and then after that, you'll be doing the lab. And I should point out there are 2 computer vision assignments that you must do before you do the computer vision lab, because those assignments will build up your experience in doing computer vision software. So when you end up doing the computer vision, the robot vision lab, you'll already have some experience with computer vision software. Okay, so that's the vision piece. There are other sensors that we use on the body. I mentioned how important hearing is, or whether we're mimicking human hearing with microphones and using high quality microphones. And there are systems out there that can identify location based on microphones. I think the most common application that you probably read about in the news is that many police departments use systems for identifying where there are gunshots by having microphones distributed around the city. And when those microphones essentially pick up a very loud sound like a gunshot, they're able to triangulate and locate where that gunshot was so that the police can get there ASAP. So that is one application, high-tech application, very useful for crime fighting. But again, there are many other applications. Certain sounds may be very important for a robot application. Touch, as I've mentioned the other day, we have 2 abilities, certainly. And by the way, there are touch sensors, tactile pads. Some robots come with them, or you can buy them separately, where you use, where essentially pressing down on the finger, and you can then measure, based on the pressure and the cross-sectional area of the pad, how much force is being applied. Or the fingernail essentially is a very great amplifier for very small changes, so that if you rub your fingernail over different roughnesses, then you're able to figure out what the surface roughness is for a part. So touch also is important. Balance is critical. You saw the Digit robot. By the way, somebody answered the question how much that Digit robot cost. Ford bought 2 of them. Each of them were $250,000. I guarantee you that the Boston Dynamics Atlas is in the millions. So I don't know how much. It's not commercially available. But the Digit robot was $250,000 sometime in this past year, to give you some frame of reference. Anyway, machines like that need balance. Balance is extremely important. How do humans measure balance? Anybody have any idea? Yes?
The inner ear.
The inner ear, the vestibular system, which is located down inside the ear canal. The vestibular system essentially is like a spiral tube, and inside that spiral tube is a liquid. And there are little hair follicles inside which are extremely sensitive, so that as you move your head around, that fluid sloshes around and stimulates different nerve endings on these follicles inside the vestibular channel. And that gives you a sense of how you're oriented, and then you can essentially compensate that using your legs, using whatever, your torso, in order to stay straight. This is an extremely important function, and I don't know how many of you go diving, scuba diving, or if you go scuba diving initially in cold water, what typically happens is your vestibular system doesn't work very well because it's way too cold for them to react. And so how do you compensate in order to know which way is up? Anybody a scuba diver? Anyone? Louder if you're saying something. Bubbles, right. You essentially look around you at the bubbles, and bubbles are always going up to the surface. So if you want to know which way is up, you just follow the bubbles up to the surface. But again, very important to know which way is up and vertical. And that is going to become very important because we're going to define some coordinate frames based on the vertical axis, which way is up. And we're going to define yaw as a rotation, right-hand rule rotation. We're going to define yaw as an angle about a vertical axis. So we'll talk about that later. But again, balance is extremely important. And how many of you ever heard of a neurologist by the name of Sachs? There have been several movies about him. He's written a book about the man who mistook his wife for a hat. Essentially, in there, it's a bunch of short stories, and one of the stories is about a carpenter who essentially lost his sense of balance, some neurological disease or whatever that affected his vestibular system, did not know which way is up, and he was always walking at a tilt. And what he did, a very smart fellow, he basically put a little pendulum in front on it, mounted on glasses, and initially he could see the pendulum and then was able to straighten himself out by monitoring the direction of the pendulum. So we are very adaptive creatures, and we can use our brains to sort of compensate for some of these misalignments, so to speak, in what we see. So again, balance is extremely important, and there's lots of pathological conditions that will affect balance, and it's an incredibly important thing for robots, but certainly important for humans as well. Proprioception. Anyone have any idea what I'm talking about when I say proprioception? Some people moving their arms around. Proprioception is essentially the sensory capability that you know where your limbs are, even if you don't see them. You put your arm behind your back. How do you know where your fingers are? But don't you know where your fingers are? All of you know where your fingers are. Why? Because we have several different kinds of sensors internally. There are sensors that measure muscle length. They're called spindles, muscle spindles. They're located in the fibers of the muscle, and essentially think of them as a spring that extends and contracts. And as that spring extends and contracts, it sends signals back to the brain. And you are able to essentially identify where your muscles are, and by essentially extrapolating that, you can then figure out where your limbs are. So I can tell, without looking at my arm, I can tell where roughly what the joint angle is. I don't have to look at it to know that it's now extended 180 degrees, now it's 90 degrees, etc. I can move my arm around without looking at it. Hey, I know where my arm is. You don't even think about that, but how would you know where it is if you didn't have some sensory capabilities to figure that out? Another important sense is to be able to know how much force you're applying. How is it that you're able to go into the grocery store and pick up now it's a 4-pound bag of sugar, and distinguish it from an 8 or 10-pound bag of sugar? You don't have to sort of look at it. You kind of know how heavy it is. How do you measure forces? Well, essentially, there are muscles. The muscles connect to a tendon, and the tendons insert into the bone. And in those tendons, there are what are called Golgi tendon organs. And essentially, when you apply force to them, they send a signal back through the nervous system to identify how much tension, how much force is in that tendon. And again, you essentially use that part of your brain to calculate how much force you're applying. So you have a pretty good sense of how much force you're applying, and you have a pretty good sense of where your arms are. And these are two very important sensory capabilities that we absolutely need to duplicate in a robot. All right? Certainly, think of a position feedback system. We need to be able to know what the position is in order to control position, as all of you should be familiar. So another term that's often used instead of proprioception is kinesthetic feedback. And kinesthetic feedback is pretty much the same as proprioception. Then let's not forget temperature. How is temperature important for the survival of humans? Again, not all sensors are meant for control purposes. Sometimes they're just basically for self-preservation. Temperature is extremely important for the human body. We are warm-blooded animals, and we maintain our temperature at a very constant level. These days, everybody's shooting a temperature sensor at your forehead in order to figure out what your body temperature is. But if we aren't controlling our body temperature, we can be in trouble. If your body temperature goes to 103 or 104 degrees Fahrenheit, you're in trouble. That means you're very sick. And what does that temperature tell you? That means your white blood cells and everything else is really fighting very hard against whatever is in your body that you want to remove, and that elevates the temperature of your body. And there are lots of theories about how this temperature elevation fights whatever pathogens are inside the body. But the bottom line is, if you are really at a high temperatures, you cannot survive 105 degree temperatures. You might spike for a minute, but I think you die very quickly at those very high temperatures. So temperature is very important for self-preservation. And if you go outside at sub-zero, your mom once probably told you, wear a hat. That's very good advice. Why did you get that advice to wear a hat? Anyone have? Yes? You lose a lot of body heat to your head. But why is that? How does that work? Yes.
Your brain consumes a lot of the body's energy, like 20%.
Well, that's essentially what happens is your brain has the top priority for blood. And essentially, it's going to keep pumping blood up into your brain, in other words, to maintain a certain temperature for your brain. And so all the heat conducted through the blood is moving up to your head. And if you don't insulate your head to keep that blood temperature at a reasonable level, what's going to happen is you're going to essentially pass out. That's how people die out there. Okay? When you're out there, I don't know how long you can survive in temperature like that. You're just going to black out, and that's going to be it. So why is it that when you look at somebody and it's very cold out there and they're not properly clothed, their lips turn blue? Or your skin turns kind of bluish? Well, essentially, we have very small micro blood vessels that are near the surface of the skin. And essentially, when you're very hot in the summertime, you get flushed. What does being flushed mean? That means your blood capillaries dilate near the surface of your skin, and so you look red because your blood vessels are relatively big. And what are the blood vessels trying to do? They're basically trying to cool you down. So getting the blood vessels close to your skin, the whole point is to try to cool you down. When you're very cold, they submerge. They submerge and they constrict. Instead of dilating, they constrict. They submerge in your skin, and all this is taking place, again, to keep your body warm, essentially to keep your core, your torso, and your brain as warm as possible. So again, temperature sensing, you may not think of it as a very important function for robots, but it's a very important function for humans. And if your robot is involved in cooking and in baking, hey, temperature sensing becomes very important. And how does temperature get controlled? Again, I don't want to get into all the details right now. We'll talk about all this still. I'm going to take a break now. I see it's 9:07 a.m. Why don't we resume at 9:17? In 10 minutes, we'll resume the class. And hopefully I'll check if the lab schedules have been updated by... Is Hayoung Jung here? No. Okay. So why don't we talk, Timothy, and we'll fill you in on a lab schedule. Thanks. We'll meet again at 9:17. I'm looking if Miranda sent me an email with an update. I don't want to... Let me say whether they're based on the recent submission. Still nothing from Hayoung Jung. Let me shut this off. I don't think the world has to hear. Yes.
Hey, I was yesterday. I had a
Okay, did you...
I emailed you. I didn't know.
It's not TA. Miranda in the undergraduate office is taking care of it. I'll tell you what.
I refilled out the Google form again.
I did.
Okay, let me see. Well, let's... I just checked in with her, and let me disconnect from the world. Give me a chance, and I will...
I guess I have. Oh.
You guys see your troops? You guys, I know I saw that. I just saw that. Yeah, I live next.
We'll fill you in.
I was talking with her the other night about which one she should take. She wasn't sure.
I got like my fourth or fifth.
The Ford truck one is first, so like, I was like, there's no way I'm getting it, but I'll do it anyway.
Right. You never know.
Alpha
Someone has to get it.
Diane got it. She said she wrote a paragraph on why she wanted that one. I'm like, oh, that's why I didn't get it. I didn't write anything.
I got blood vessels.
I don't remember what that one is. I kind of
I think it's like something like which like blood vessels like external or something. It was one of the ones that I like put on randomly because I was random options.
you didn't like those five of them?
Not all of them, like a few, like 3 or 2.
Okay, I have the latest schedule. What is your name? Andrew Urban. I see you are now scheduled on Wednesday, 1:25 to 3.
Yep.
So she saw you. Okay?
Yep.
And you're Timothy.
I wrote, I'm really like,
Look at where you are. Is that good?
I think so. Yep.
It's a good slide?
Yep.
Okay, so this will be the lab schedule. I'm now going to save this and post it to...
I
killed every
I definitely
You
waited.
good?
Like my 5 options, I didn't even ask anyone else if they'd put. I didn't request anybody. I'm just like, hopefully this works out. And it worked out. So I know 3 of the other 4 people. I'm like,
I know, I was like, oh, shit. That was kind of a shock. It's like,
yeah, that's cool.
she's gonna have some creative ideas, I feel like. So.
Yeah. I was looking, you guys got the diamond one. I looked at that too, but then I'm like, I feel like the prompt is so vague. So I didn't. But I definitely had that one.
I think it'll be interesting. I like the idea of like, it's like half a networking opportunity and half like a project. So it's like,
What has this?
new company and the project.
I want to uninstall it.
Like, create a new process.
It's just 3M, right?
Pretty generally of like the project itself. No huge complaints. It wasn't our first choice for sure.
What was your first one?
Like the Clapper.
Probably a really popular one.
It's the only biomed one that I put. I put the Gender Mills one out well.
Nice.
Will they rehire me? I was like, but maybe I don't want this one because I could literally get paid to do it. So
Oh,
if
yeah.
I do it for free, and I could.
And why not take the opportunity to do this next year?
Just a witch.
I mean, I didn't find it because I'd rather do something I want to do.
I'm glad I got the one I did, just like manufacturing. It's like they want to fix something in like one of the machines they use for like just the
Is it
manufacturing.
the case pattern? Who's the
Yeah,
company?
it's like the dairy conveyor
Yep.
belt one. Yeah.
I'm familiar with case packers because
Yeah, I couldn't quite understand exactly what they're saying the problem was. They said it kind of vague in like 1 or 2 sentences, but it sounded like maybe like a machine or a piece of equipment that they just didn't quite feel comfortable with.
the case packers are typically a huge point of like they go down almost, at least on the line I was on. So you constantly have to be like fixing them. I don't know what specifically.
There's like they said you could do a site tour with it too, which I thought that was cool.
People need to probably, otherwise
Yeah, I like that.
I put it on my list too.
Yeah, I saw that and I'm like, ooh, I'd really love to see that.
Oh yeah, they're sweet. Well, it's like you put the product in like cartons or boxes, and then pack them into cases. So usually how they work is like suction, like put it in the box, and then close it off.
So
That's a
what
pretty
part
cool.
of that like is the problem then? Because they're saying something like gets in the way, or like something They want it so that if like something goes wrong, it doesn't disrupt the rest of the processes.
Yeah, it's probably like something could fall off. And we had a problem with a different machine. Like if stuff falls off and you lose that piece, or it damages another piece, then it's really very because we lost something and I spent a lot of time looking in our, I think it was like our carton packer, so the step before the case packer. But yeah, it's like all that stuff can break and then you're just screwed. I don't remember exactly what it was, but
Someone interested in doing this.
I think it'll be actually a really good
Because
Yeah, I'm excited.
on my
I have
list.
a pretty good group and I've had a cool project, so I'm pretty happy. It worked out for me.
And it's really like yeah. Those machines are
I did take a look at their website, but I didn't really dive into it, but it probably will now.
Oh yeah, I mean I didn't really either. I'm jealous. You'll have to take a picture for me. I know that's like really illegal, but well maybe not. Well, it depends what kind of case.
Well, you've seen all like the General Mills.
I know, and I'm really bad about shutting up about things. I need to be quieter. But I mean, yeah, they're like massive. They're packing like the larger cases. Because I worked on the Nature Valley Live, so cartons of 6, 12. And they have cases. That's I guess it depends, maybe.
Get a goal. I think he only played like 6 hours.
Is it weird to like sit on a card that you would fall on?
People do it with like Mega Knights. They save them until like 30 seconds. And I just like, where is this one?
Yeah, exactly. This seems to work.
Just go work.
I feel like most of the questions a lot of the questions I definitely not saying oh yeah, he sent me his diet. It's pretty good. No, I mean it's like yep. But like I can also see like I know it's
No, it's gonna die.
I can tell it's like literally
They use 12 to stop your 12, sir.
And you can probably move back to corporate if you're not.
I got these two.
I'll have to ask you.
I work for it wasn't entirely.
Okay. What I was busy working on was kind of finalizing a lab schedule. All right, why don't you take a look at it right now? I don't know if you're going to find your name and time here, but as soon as class is over, I will post this lab schedule on. Oh, sorry. As soon as class is over, I will post this as an announcement on Canvas. So you can all. The only person who I don't know about and has not yet responded is Hayoung Jung. Everybody else who's signed up for the class is listed here and is scheduled. Obviously, if Hayoung Jung comes along, we're going to have an odd person, and I will have to add a third person to a lab group. But I'm not concerned right now. Yes?
I'm on there twice.
You are? What is your name?
Very first schedule on Monday, and then the second slot on Monday as well.
Okay, we'll see if we can figure that out. John Haney.
Yeah, I got 2 labs to do.
No, you only get one. So you're on, which do you prefer?
Keep me on the early one, why not?
Stay on Monday. And which one should you be removed from? Where are you?
The 125 to 320.
125 to, oh, I see. Huh. Okay. We'll, so you want the first slot and get rid of the second one.
She was.
Okay. I will do that. Again, I will fix this before we post it, okay? So there's no confusion. What this means is I am going to remove John Haney from the second slot, which means the 3 of you, for time being, will be in a lab together on Monday. That's Kyle Johnson, Min Huang, and Arun Cherkel. I'm assuming what typically happens, somebody's going to drop the class probably in week 2 or week 3. It always happens. And so whatever group of 3, I will then move one of you to another time slot. So just for the first week, which is next week, stick to the schedule that I will post. Again, I will post it on Canvas after class is over. So any other inconsistencies or issues that anybody sees right now? Okay, everybody found their name? Okay, I will post this and I will remove John Haney from the second slot, and that means the group of 3 will stay where they are on the 1:25 to 3:20 p.m. slot on Monday. All right? If any of you drop the class, I've had this problem before, you drop the class and I have no clue that you've dropped the class, that creates a problem for your lab partner. Please, as soon as you decide to drop, be courteous to your lab partner. Let them know that you're dropping the class and send me an email as soon as you know so I can help rearrange the lab times so that we have essentially everybody's scheduled for a lab slot. Any questions? Okay. All right. Good. So let me go back to my notes. By the way, you'll notice that I've already loaded my next lecture because I wasn't sure how much time. I'm never quite sure exactly how much I'll cover in a particular lecture. We're over here. So lecture, it's not really lecture number 2 itself. It's just my set of lecture notes. That's the second set of lecture notes. Anyway, we talked about temperature. Smell and taste are other senses that humans have. Very important. Essentially, our olfactory sensors, which we use for smell, again, are in the back part of the nose, deep inside. And clearly with COVID, that's been one of the incredible symptoms that's been directly associated with COVID or long COVID, losing that sense of smell. Smell is incredibly critical. It affects your taste also. They're intercoupled. Smell and taste do come together. But without your sense of smell, there are all sorts of issues related to carbon monoxide, and there are all sorts of other things. That smell is very important to tell you there is a problem. So I call smell and taste and pain and temperature as self-preservation sensors, self-aware sensors, sensors that are incredibly important for you to know that you've got a problem and you've got to take care of that problem appropriately. And the same thing goes for robots. There ought to be sensors that let them know that a finger is broken off. It happens. It happens all the time. That you've applied too much force in some way and a joint is broken or something is dead. And a lot of robots don't have, they may break, but they don't tell the programmer, or the program doesn't check that the sensors are all operational. So again, self-awareness sensors that tell the machine or the intelligent part of the machine to compensate is incredibly important. And you as robot designers and programmers need to build that into the technology. And then let me not forget pain. You might think that, boy, wouldn't it be great if I didn't have any pain sensors? They're probably the most important sensor that you have in your body. And you might say, why? Well, just imagine if you didn't know about a toothache. I mean, that's probably the most common pain that you will feel. That tells you there's a problem that you need to take care of. So having a sense of pain sensors are important so that you can identify where the problem is, and you can tell your dentist where the pain is so that that person can take care of your problem. And it's not just pain in your mouth. There's all sorts of other places. You wouldn't know that your bone is broken if you didn't feel pain. Again, so having a sense of pain is incredibly important. And there is a human pathology. Certain neurological conditions eliminate your ability to sense pain. And that's horrible. A good example are paraplegics and quadriplegics, who essentially, let's assume for a paraplegic or quadriplegic who is lying there on a bed or been put into a chair, and they're sitting in one spot. You know that you are constantly moving your butt around so that you don't apply pressure to the same place. Because if you don't do that, you're going to develop what's called a pressure sore. Literally, the skin will break apart because too much pressure in one spot, there's no blood flow in that area, and you are going to develop terrible pressure sores. And if you've ever seen pictures of pressure sores, they're awful, and surgically they have to be removed. So again, you must have a sense of pain. It's important for self-preservation to know that I am in pain and where the pain is so you can do something about it. And again, if the nerves that sense pain and don't send that information back to you, if they're not functional, you're in deep trouble. So please, when we talk about designing robots, how do you mimic pain? You know, that's really a tough call. How do we create the ability for the robot to sense that something is wrong inside their machine? And most robots today have very limited capability of doing that. And I might say one of the reasons we use a cobot in the lab is they are probably more self-aware than most other robots. They will stop working. In other words, they'll stop when they hit a wall. And, you know, essentially way back when we had an experiment in the lab to do that, they are so fast, the cobot response characteristics are so fast that it became difficult for us to sample the load cells fast enough in order to recognize how fast that they were reacting. We decided we'd just demonstrate it, as you saw in the film, in the video before, rather than you're doing an experiment, because when you guys were doing the experiments using an Arduino processor, it just wasn't fast enough to keep track. And so we decided we'll just take that lab out and we'll just show you the demo. So with that, we need to move to the next level, which is essentially what do you do with all this information and how do you process it? So there's the human intelligence part. And, what is human intelligence? It's, that's really hard to characterize. But the neurologists and psychologists and, cognitive psychologists, they essentially have tried to understand where different intelligent, what we would call intelligent, where that functionality sits, where it resides. And essentially, again, very simplistic model, very simplistic. Essentially, we have the main cortex of our brain, which we typically call the cerebrum. That's where your high-level, important decision-making takes place. The complex decisions as to, should I get up this morning, or really, do I need to go to class or not? That's a complex decision where you can't write an algorithm or an equation to solve that. Then there's the cerebellum. The cerebellum is in the back part of the brain. Essentially, your spinal cord and all the nerves that travel up your spinal cord basically feed into the cerebellum. The cerebellum is the coordinator, if you will. That's essentially that coordinates all the joints and all the muscles in order to do a particular task. So I don't have a spoon here, but if I had a spoon and I had the spoon full of soup and I wanted to make sure that I was able, without spilling, able to coordinate all the muscles and joints in my arm and not spill anything, essentially it is the cerebellum that coordinates all the forces and muscles in order to move your spoon and do a very delicate activity. The cerebellum is associated with coordination. Then the spinal cord, there are afferent and efferent nerves, essentially nerves that go out and activate the muscles to contract and do something. And then there are the nerves that bring the information from the tendon organs, from the muscle spindles, and bring them back to the spinal cord. And there is a very fast, complex reflex activity that as an infant, you already have these reflex activities. And some of those reflexes disappear as you grow older. Some of those reflex activities still exist even as an adult. You go in for a physical, your physician basically takes a little hammer and bangs your knee, and your foot moves in response. That's a reflex activity, a very fast reaction. And we all have those reflex activities. We used to have many more as infants, and many of them went away as we grow older. But again, that closed-loop feedback is essential, and in robots, that's the position control, the velocity control, and PID, PD. Again, when I'm going to talk about PD control, and later we'll talk about it, we're mimicking what's going on in the human body. We don't, some people say they really understand everything there is to know about how we control our arms and fingers and everything. I'm not sure we're there yet. So what we do with our feedback controllers is we're trying to mimic, duplicate the best of our knowledge, how we control our fingers and arms and wrists, etc., etc. Again, as we move down this arrow, we essentially increase the precision. In other words, ability to keep a spoon of liquid balanced appropriately requires high speed and precision, but it's not a very complex activity. But up here is where we make the big decisions. If I see somebody approaching me on this side of the street, I don't want to talk to them today. You cross the street or whatever, or basically move into a crowd so they don't see you. I mean, that's a very complex activity based on your perception and your experience and what you want to accomplish and do that particular day. That's what we mean. And those complex decisions are taking place in your cerebrum. Again, there's lots of stuff, and and how we. I'll give you another example of a very complex activity. When I'm writing with my pen on this particular surface, if I push down too hard on the surface, I'll rip the paper. If I don't push hard enough, the ink won't roll out of the ballpoint or the gel or whatever kind of pen you're using. So controlling the force and the position simultaneously is a very important function when we're handwriting, okay? And so keep that in mind as we do various tasks. If the task for the robot to do writing, there's a lot that goes into a robot writing cursive on a piece of paper. That doesn't seem so obvious, but it's a big deal. So we're going to break down human activity into what the medical world calls gross motor activities. Usually physical therapists deal with that kind of issue in humans. And then there's the fine motor activity, which is controlling your fingers, your arms, doing very fine motor skills. And there's a different class of paramedic person, an occupational therapist, who typically deals with patients who have problems with being able to control fine motor activity. In this class, we are going to focus mostly on manipulation. We are not going to get into walking robots. We're not going to get into balancing machines. There's a lot of very interesting stuff there, but we're going to focus on the manipulation world in this particular class. Although every now and then, if you look at previous exams, and by the way, we put, I think, about 10 years worth of exams are more exams than you really want to look at. We put the exams and the solutions posted on the website. And if you look back, some of the problems deal with a leg of a particular robot, but because it's just a suitable place to look at coordinate frames and how coordinate frames interact with each other. And so we might use a leg for a problem in figuring out coordinate frames, etc. But for the most part, when we talk about manipulation, is what we're going to focus on in this class. We're going to be dealing with revolute joints. That's a hinge joint, if you will. The door has a hinge joint. It swings. That's a revolute joint here where my elbow is swinging out. That's a pure revolute joint. And then we're going to have prismatic joints, which are just extension devices that move in and out. If we take a look at this pen, think of this as a prismatic joint. That could be a pneumatic actuator, could be an electric actuator, could be a hydraulic actuator. Essentially, this is a prismatic joint. So we're going to build up our robots using revolute joints and prismatic joints. We're going to typically talk about a revolute joint and use the R designation for a revolute joint and P for a prismatic joint. And then by combining these joints, we end up with different classes of robots. So a rectangular or Cartesian robot essentially is going to have the motors that are driving it. There's a prismatic joint in this direction, another prismatic joint in that direction, and a third prismatic joint in the Z. So we directly control the X, Y, and Z by motors that are driving the robot directly along X, Y, and Z. But there are also spherical robots. Spherical robots have been used for a very long time for welding. In fact, if you look at all the classic videos of automotive manufacture where they have to do lots of welding, they use these kinds of robots typically. Again, there's an angle that allows you to move off the horizontal plane up. And that's one joint, one revolute joint. And then there's going to be another joint, which is a rotation about the Z direction. So essentially, by having a rotation in this direction plus a rotation in that direction, you essentially get 2 degrees of freedom. And then if I have a prismatic joint in this direction, I will get a 3rd degree of freedom. Those 3 degrees of freedom is essentially, basically, it's an RRP robot. So we can control, with 3 degrees of freedom, we can control the X, Y, and Z position of this point over there. We aren't yet controlling the hand. And there's a wrist rotations that we're going to talk about later. But just to control where the wrist is, this one we do X, Y, and Z. This one we essentially have angle 1, angle 2, and a prismatic distance motion. Then this is a cylindrical robot. In a cylindrical robot, we put our revolute joints and prismatic joints differently. In this case, we have one prismatic joint which is in the vertical direction. We have another prismatic joint which is in this direction. And then there is a rotation about the vertical. And combining essentially P, then R, then P is going to give us, again, control of where the wrist is going to be. So we're able to control the X, Y, and Z of the wrist by controlling 2 prismatic joints and 1 revolute joint. Does that make sense? Okay, does that give you some sense? So here's a very simple old robot. General Electric, once upon a time, was in the robot business. Every company changes over the years. And they made a very simple robot. I don't remember what the model number was. But here was a table. And so you had X along this direction, Z along this direction, and Y along this direction. And then there were 2 wrist joints, R1 and R2. Again, I don't want to get into any conventions about defining R1 and R2. But for right now, it was very simple to control where the wrist was on the robot. You just entered your X, Y, and Z, and you directly controlled the position of the X, Y, and Z. Well, this was a very simple controller. This is a copy out of a manual for that particular robot from way back when. Hard to find old manuals anymore, and I don't even own them. Maybe somewhere I have them. But essentially, what was involved, each joint had an 8-bit processor. 8080 was an Intel 8-bit processor decades ago, and each joint was controlled by its own 8-bit processor. So there was the axis motion, and there were transducers on the arm, and they brought feedback. And so each joint was controlled by an 8080 8-bit processor. And this LSI was manufactured by a company called Digital Equipment Corporation, DEC. I don't even think they exist anymore. An old Boston company. This was a 16-bit processor. And what did this 16-bit processor do? It coordinated the multiple joints out there, and it did some syntax processing. So you had some language, a very simple language of some sort, and it was able basically to take that syntax, break down what you're trying to do, and then send signals to each of the joints to the 8080, and with all that feedback, you close the loop. And then there was a separate controller from the LSI 11, again, a 16-bit processor of several decades back, and it controlled the gripper as well, and there were sensors, and then there was feedback. So, and this was really an old peripheral, let's call it that. Way back when, floppy disk, anyone even remember what a floppy disk was? I still have some just for memory's sake. So anyway, this was a simple robot. We're going to talk about much more complex machines in this class, and so we have to get into much more complicated issues. We're going to be talking a lot about articulated manipulators, manipulators that have what looks like an elbow, looks like a shoulder, looks like a wrist, and that gives you a lot of flexibility and dexterity. And well, I shouldn't say most, but a large significant number of robots have an articulated geometry like you see over here. Not all. For certain functions we're going to see other kinds of configurations. There are many different ways that you can slap the Revolute joints and prismatic joints together to get different functionalities and different motions. This particular kind of robot was very popular for several decades, and the company that made this robot, Cincinnati Millicron, they're still in the business of making machine tools today. I don't know that they make robots anymore, but again, somebody can look that up and correct me if I'm wrong. This was a hydraulic arm, and you can see the hydraulic actuators. So keep in mind, this is a hydraulic actuator, which is really a prismatic device. It's a prismatic actuator, but what it's doing is it's causing a rotation of the elbow joint. So when we talk about this kind of robot, we don't get into the nitty-gritty. I mean, obviously in the controller, you're really controlling a hydraulic linear actuator, but by controlling that hydraulic linear actuator, you are in effect controlling a joint angle. So we could still classify this robot as having Revolute joints. So there is going to be a shoulder here. There's going to be 1 degree of freedom, which is a rotation about a vertical axis. Another degree of freedom is a rotation about the axis of this motor over here. So this might be joint angle 2. This is the elbow, which we might call joint angle 3. And then down here, there's going to be a whole bunch of joints, which we will call joints 4, 5, and 6, depending on what we're talking about. Now, this kind of robot is also used for welding, spot welding. For instance, this might be a weldment, and this would be the torch, and we are essentially going to weld several parts together, and we need to move along a straight line. So the path that we have to control that weld torch, we have to make sure that it moves continuously at constant speed as it follows the path of that particular weldment, okay? So in Cartesian space, we are going to define the position of this particular path. We have to control the orientation of the torch to make sure that it is applying its heat, so to speak, in a continuous fashion. If we aren't continuously moving at constant velocity, what could happen if there's too much heat at one particular spot? We could blow a hole through the weldment. And if we don't go fast enough, we're going to get a cold weld, which is a very poor structural issue. So essentially, we have to control the velocity of the tool as it moves down and does the weld. We are going to be talking about all these issues. How do you do all that? That's going to take us into the mathematics of controlling velocities, positions, and breaking that all down. What's most important, let me see what time it is. Okay. Is how do we, you all know how to by defining position, X, Y, and Z, and we're going to use the right-hand rule in all cases. All right, so essentially, when I talk about X, Y, and Z, if this arm, and I'm going to stand up now, if this arm is X, okay, Y is this, so X to Y, right-hand rule, so that think about a vertical axis through my head going up to the sky. Essentially, X goes to Y, right-hand rule. Z is in this direction. All right? Now, roll, pitch, and yaw, the convention I like, which we will use, but the textbook has different versions, and certainly Universal Robots likes a different convention. But essentially, we are going to call the term yaw as a rotation about a vertical axis. So there are two different things. There's X, Y, and Z, and then we have to define 3 different angles, because to define the position and orientation of something in space, okay, if I have this pen, if I just give you the X, Y, Z location of this pen, all that means is I'm defining one point on this pen. It's a rigid body, okay? I could still have this body oriented in many different directions about that point. Well, let's say I define 2 points on the body. So I know the XYZ location at that point. I know the XYZ location at this point. I can still rotate the pen between those 2 points. I need to know the XYZ location of 3 points on a rigid body in order to uniquely define where that rigid body is in space. Okay? But that doesn't mean that knowing the XYZ of 3 points on the body, that I always need just that information to define the position and orientation. Sometimes all I need is the XYZ location of 1 point on this body, and then I need to know the roll, pitch, and yaw of the rest of the body. And so what do I mean by roll, pitch, and yaw? We're going to do, getting back to the screen here, so we're typically going to talk about yaw as very similar to airplanes and how they define roll, pitch, and yaw for an airplane. And I find, and others have found, that that's a very useful way of defining orientation. Is yaw is a rotation about a vertical axis. Okay? That's so how do we know what's vertical? Well, in almost all circumstances in a manufacturing world, we know what is vertical. We have a table. Okay? I'm assuming you set up the workbench, so it defines a plane, and we usually think of that plane as a horizontal plane. So when we talk about yaw, it's a rotation about a vertical axis, which is going to be, the vertical axis is always going to be perpendicular to a horizontal plane. So essentially, we can define the other two axes that you see over here as those two axes are sitting in a horizontal plane, and pitch is going to be the angle you make with respect to the horizontal plane. Okay? So if this is a horizontal plane, this is going to be pitch, either down or up. And again, that's going to be a convention, which should be positive, which should be negative, and essentially we're going to define those conventions. And so pitch is always going to be, always, in our convention, is going to be an angle with respect to the horizontal plane. And then roll is the last part of it, and that's going to be so here's my x, z goes this way, x, y, z. So essentially yaw is this. Pitch is that, again with respect to the horizontal plane. And then the last but not least is going to be what we call the roll, which is essentially going to be a rotation about the z, and so we're going to get this. So if you think about an airplane, and then we have to define coordinate frames with respect to the gripper, with respect to the tool. If you saw Nick Arsvold and his presentation before, typically we take a gripper and attach it to a plate on the end of the robot. The flange plate, when we attach it, usually at that tool Z comes out of it. And if you look at that flange plate, it's typically going to have an X and Y associated with it. You look at the manual of the robot, they'll always tell you where the X and Y is on the plane. And now you begin to be able to define everything you need to make sure that you move. On an airplane, when you're sitting on an airplane, and I think that's probably the most common exercise, all of you have been on an airplane. When we talk about pitch, that means we're making a descent or we're taking off. So the pitch angle is going to affect how the plane is oriented in that direction. When we talk about yaw, that means the plane is essentially turning this way or that way. And roll, when you're sitting on a plane, the fuselage, which is essentially all the seats sit one in front of the other, the roll is this rotation. If I'm sitting in my chair on the plane, this is roll, essentially. If I'm sitting in my seat, this is going to be yaw, and pitch is going to be that kind of motion. Anyway, roll, pitch, and yaw, in that definition used by the airplane people, aircraft, that is one that I think is very useful to use, but you'll see other definitions as we move on with class. Essentially, we're about to run out of time, but we're going to be using a Puma 560 for a lot of our analysis. It's it's kind of it's been around a very long time, and you can actually look up Wikipedia to look at the history of this particular kind of robot. This is what it looks like over here. It's got a shoulder, it's got the trunk, there are motors, and why I like to use it is because we used to have a whole bunch of them in the lab, and as they broke, nothing lasts forever, I took them apart and I took pictures of the insides. And it's very educational for you to see what the transmissions look like inside the robot. So I spend a lot of time on this robot, and if you're wondering why do I use this old classic robot that you probably can't find anymore, it's because I have pictures of the anatomy. And as mechanical engineers, I think it's extremely important that you understand how these machines are designed internally so that you can figure them out and learn in the future. Yes, you might be designing a new UR, whatever, a new cobot in a different way. And clearly the UR5 does not follow the kinematics of a Puma robot. I'll tell you right now, and we're going to get into all these details in the course of this year. And I know we're running out of time. So anyway, I thank you for your patience. And I will be posting the lab assignments shortly. Give me some time to get back to my office and set everything up. By the way, just in case I haven't mentioned it, my office hours, I'm just going to repeat, will be on Zoom. I will post the Zoom schedule. And one other thing, I just want to remind you, I'm going to be posting a Google form for submitting pictures of you. So I begin to learn who is who. Over the course of the semester, maybe I'll remember a few names. Okay? Take care. Have a good rest of your day. Stay warm.
Switch classes.
It's too heavy.
That's our project numbers.
No, our table numbers for things are back.
Oh.
No, we're just discussing our two different projects that are meeting with the same guy. Oh.
发短信才能不回复，我是发的那个意思。